Greetings, folks. Well, we've talked about electric fields and we've talked about electrical potential fields or voltage fields, sort of in their generic form. Now it's time to talk about a very special situation, which is to say electric fields, and for that matter potential fields, that are associated with point charges. This particular video is going to zero in on electric fields of point charges. The electrical potential fields we'll talk about later. Here's the template that we started with a couple of videos ago. Here is the information, the generic information for what's going on with electric fields. Here is the generic information for what's going on with electrical potentials. What we're about to do is to look to see how these quantities fare when you're looking at a very specific situation, which is to say when you're looking at a point charge. This particular video is going to zero in on the electric field of a point charge. So here we have a point charge, and here are its electric field lines radiating outward. And I'm going to place a charge Q R units away from it. You know from class that there is a Coulomb force on that charge whose magnitude is going to end up equaling KQQ over R squared. So as I said, this relationship is really only useful if you're trying to figure out the magnitude, which is to say you don't include the sign of Q or Q. If the field producing charge is negative, you do not include the negative sign when you use this relationship. All you're trying to do is to figure out how big the force is between the two charges. As for the direction of the force, that's going to be determined by whether or not Q is attracted or repulsed by the field producing charge. That attraction or repulsion is going to end up motivating the charge Q in one direction or the other relative to your coordinate axis. That's going to end up showing whether that force is positive or negative. It's also going to identify what the unit vector is that should go along with the force. So as an example, let's assume that the field producing charge is positive and that the charge that's going to end up feeling the effect out here is negative. Our relationship up here is going to allow us to determine how large a force the field producing charge is going to end up exerting on this minus Q. And by using our head, we can see that if this is positive and this is negative, there's going to be an attraction between the two, which means the force on the negative charge here is going to be in this direction. This is in the negative I direction. That would be the direction of the force. On the other hand, if the charge had been R units to the left of the field producing charge, again, you would have had attraction between the opposite charges, but in this case, that attraction would have motivated Q1 to be pulled to the right in the positive I direction. And so in that case, this would have been the magnitude once again, but the unit vector associated with the force would have been plus I. Bottom line, you use the relationship to figure out the magnitude of the force. You use your head and whether you're looking at an attraction or repulsion between the charges to figure out the direction relative to the coordinate axis you're dealing with of the force. So having established Coulomb's law, consider now you've got your charge here and there's a point out in space. There's nothing at the point, there's just a point out in space. You want to identify where the point is with a vector R. The electric field at that point is going to tell you how much force per unit charge is available at that point. Put a little differently, if you put a point charge right there and you identified how large the force there was on that point charge, and I might add, we have that quantity right here, it's the Coulomb force, and then divided out the size of the charge that was feeling the effect, which was effectively plink off this Q, what we would be left with would simply be KQ over R squared, which would be the electric field function for a point charge. In other words, we'd actually have a function that would be such that if we put in the size of the point charge that was producing the field and divided by the distance out that we wanted to go, quantity squared, it would give us a number that would tell us how much force per unit charge was available at that point, R units out, as a consequence of the presence of that point charge. And backtracking with that electric field function, we can now rewrite this side to say that the force on the charge is going to end up equaling Q times the electric field, which is Q times the electric field, where the electric field is K times the field producing charge divided by R squared. So let's look at a problem. You're given a negative charge Q sitting here at the origin of this coordinate axis. You want to know what the electric field is A meters directly below the charge. So here we are, A meters directly below the charge. You want to know what the electric field is at that point. You determine the magnitude by figuring out the magnitude of K times the field producing charge divided by R squared. So K, the magnitude of the charge is just Q. You don't have the negative sign carried along. It's just the magnitude. This is a magnitude divided by the distance, quantity squared. And indeed, this is minus A, but you don't even put a minus A in there because this is just a raw distance. It's just A quantity squared. To figure out the direction, you ask the question, what would a positive test charge do if you put it at that point? You can see that a positive test charge at that point would be attracted to the negative charge. It would accelerate in that direction. That's the direction of the electric field at that point, which is in the plus J direction. So you could write the electric field as a vector as KQ over A squared, that's the magnitude, in the plus J direction. Bottom line, once again, you actually need to execute two operations. You need to determine the magnitude. You need to determine the direction. So we still have our negative charge sitting up here. Now the question is, if you're given what the electric field function is, here it is, that's what we just derived, how large a force would a negative charge minus Q1 experience if it was put here at y equals minus A? So this takes us back to the relationship that we messed around with a couple of videos ago. The force on the charge is going to end up equaling the size of the charge, where you're going to include the sign in this case, times the electric field. Put the variables in, there's minus Q1, there is what the magnitude is, there is the direction. You multiply it out and you end up with a vector of K Q1 Q over A squared in the minus J direction. As I said, the sign of the field experiencing charge does tag along. This makes the force negative. And this in turn makes perfect sense. If you have a negative field producing charge and you put a negative charge here, they're going to repulse, and you would expect the force to be in the negative direction. Anyway, that's pretty much all I have to say about this set of relationships. We've been talking about electric fields and electric forces, but we've been doing it for a very specific situation, specifically that of a field producing charge that is a point charge. And that's it.